In this video, we're going to look at these simple formulas that you can use with discrete numeric probability distributions here, and we're going to apply them to a lottery ticket. Now, there are a lot of different kinds of lottery tickets, and I'm from North Carolina in the United States, and we have all kinds of different lottery tickets that we could look at here. This is their website, nceducationlottery.org. If we click games, you can see all the different kinds of games they have. They have a pick 3, a pick 4, a cash 5, a North Carolina Mega Millions, a North Carolina Powerball, Lucky for Life, and these instant scratch-off tickets. In this video, that's what we're going to look at, are these instant scratch and win or scratch and lose tickets. And we have all kinds of different amounts of money that you can pay for these kinds of tickets. You can pay $1 to get a ticket, $2, $3, $5, $10, $20, or even $30 to buy one of these tickets. Let's pick one of these $1 games to get an idea of how statistical formulas can help us understand what is going on with some of these tickets. Now, with scratch-off tickets, every one is going to be different. They're going to have different prize amounts you can win, and also different probabilities of winning these different amounts. So here are some of the $1 ones in North Carolina, and let's just pick this one here called Lucky Sevens. But the methods will be the same basically for any of these. So what do they tell us on the website? Well, the ticket price is $1. Your overall odds of winning something is 1 in 4.73. And if you really want to analyze what's going on, you need to download a little PDF here that gives you the details of what the prizes are and what the probabilities are. So in this game, we see prize amounts from $7,000 all the way down to $1. They tell us the odds. And odds are just probabilities written 1 in a certain amount. So take 1, divide it by that number, and that will tell you the probability of winning $7,000. So 1 in 640,000, not very high probability. And it tells us that also there are 18 total tickets that were printed that will win $7,000. Let's take this data over to Excel and see what we can do with it using our probability formulas. So here we have a little Excel worksheet where I have entered in that same information, and here are our probability formulas on the left. The first thing I want to do here is to check these two rules here in terms of the probabilities. Now, they don't tell you actual probabilities here. Instead, they tell you the odds. So let's convert those into probabilities so it's a little easier to see what's going on here. So let me insert, I'll just insert a column right here, insert, and we'll call this our P of X, or probability of X. So here our X's are the prize amounts. The outcome of this discrete process is going to be one of these possibilities. If we calculate the probabilities, this equals 1 divided by the odds. Okay, so 1 divided by C4, and that should not be in dollars. Let me fix that for us real quickly here. So I'll just right click, format cells, and we want a lot of decimal places since these are very small numbers, and this is not currency. So, okay. Let's see what 12 decimal places gets us. Okay, awesome. So now we can see what those probabilities are. That's actually probably a few too many decimal places for comfort, so let's just reduce that a little bit. Okay. I wanted to have plenty of decimal places so we could see some of these small probabilities, like 1 in 640,000 here. Alrighty. So, one of the first things I want to check is one of the rules, two of the rules for basic probabilities is the probabilities have to be between 0 and 1. Check. All these probabilities are between 0 and 1. The second thing is we have to make sure that these probabilities all add up to 1 if we sum them together. So let's see, that equals sum. Let's add all those probabilities up. And no, they don't add up to 1. So take a minute and think, why don't these probabilities add up to 1? Right, one possibility, the most common possibility, is left off. The most common outcome when you buy one of these tickets is that you win $0, right? And so what we need to know is, what is the probability that we win $0? And basically this 0.211 is the probability that you win something. The probability that you win some amount. Now what we want to know is, what is the probability that you win nothing? What's the probability you win 0? So we can just say the complement equals 1 minus this probability. So 0.7880674. 0.7880674. Now, if we add up all those probabilities, including 0, we will get 1, or 100% chance. Now, over here, just to make our table look nice, let's calculate the odds. So the relationship between odds and probability is actually quite simple once you get used to it. The probability, remember, is 1 divided by the odds. The odds, on the other hand, are 1 divided by the probability. So if we want to know the odds here of winning nothing, very simply, we say 1 equals 1 divided by the probability. So what this is telling us is we're going to win 0 about 1 out of every 1.27 times we play this, which is most of the time, right? Almost 80% of the time, closer to 79% of the time, we're going to win 0 when we play this game. Another thing they don't tell you, so notice they did not tell us the probability of winning nothing or the odds of winning nothing. Another thing they don't tell us is, out of all of the tickets that they print up, how many did they print that will give us 0 as our winnings? Let me give you a way to think about doing that. This is just another interesting question when it comes to these scratcher tickets. In order to figure out how many total tickets they printed, so equals, oh, I shouldn't type equals there, just total tickets. And it's kind of mind-boggling when you calculate this. For just this $1 scratch and win ticket called Lucky Sevens, in order to get the total number of tickets printed, here's a way to think about the algebra that we want to go through to figure this out. We know that 18 tickets were printed that will give us $7,000 in prizes. And we know that if we take 18 divided by the total number of tickets, that's the same as 1 in 640,000. Right? So we know that 18 out of the total number of tickets is the same as the probability 1 out of 640,000. So really what we want to do is solve for this number of tickets here. So using a little bit of algebra, we could multiply the number of tickets by both sides, and then we get 18 equals the number of tickets divided by 640,000. Multiply both sides by 640,000, and that's going to give us the number of tickets. This is the total number of tickets that they printed that has this Lucky 7 logo on it, including the ones that where you win nothing. So the total number of tickets here is going to just be equals 18 times 640,000. Let's make that a little bigger so we can actually see what that number is instead of an engineering notation. Okay, so that is 11,520,000 total tickets were printed here. Now it turns out that you can also get this number of tickets this way. I think hopefully you can see the way this formula is going to work out. All we did there really, what the math told us to do, is just take the 640,000 times 18, right? So equals 640,000 times 18. Or, sorry, let me do that as a formula here, times D4. And it turns out if you want to get that number, you can actually multiply any of these rows out, and you should get the same number, or very close, except for here there's going to be a little bit of rounding involved. So if we just copy that formula down, if we take 600 times 17,600, for example, we should always get the same number. Now, the reason we're getting slightly different numbers here is that these odds must have been rounded slightly. Although that's a bit of strange rounding here. Hold on one second, let me check into this. I'm of the opinion that this odds calculation that they gave us in that PDF is incorrect, because I have analyzed hundreds of these lottery tickets before, and I've never seen anything like this. They must have made a mistake here. So instead of there being 11,520,000 tickets, since all of these are consistent except for the last one, which is just a little bit of rounding error here, right, because of the 7.14, when they list those odds, that's not actually exact. They've rounded it. So what this is telling me is that the total number of tickets must be these numbers, 10,560,000, and that this is actually incorrect, therefore that odds is incorrect. So really, the probability here should be equals 18 divided by, so 18 tickets out of the total, 10,560,000. That's actually the correct number of for the probability, and therefore the odds are going to be equals 1 divided by the probability. So it looks like that should be odds 1 in 586,666 instead of 640,000. So that's going to change our other answers here slightly, but still pretty similar. Our probability of winning something, about 21%. Our probability of winning nothing, about 0. Okay, so we can figure out how many tickets were made, and we can even correct mistakes of the people who make these little PDFs. Another thing we might be interested in is just how many total tickets were printed with the 0 prize amount, and that's just going to be 10,560,000 minus all of these winning tickets, right? So let's just calculate that real quickly for fun. So it's the 10,560,000 minus the sum of how many winning tickets did they print. And here we see they printed up about 8,322,000 tickets that won nothing. So let's use these two formulas that we were talking about earlier. Let's calculate the expected value and the variance. So the expected value is what we get if we take each of these values for x. Again, this is the winning prize amounts, including the $0, times the probability that happens, and then we add all those up. That's going to tell us the long run average, or the expected value as we call it. And what it's going to mean in this case is if I buy one of these tickets, on average, how much do I expect to win? So let's create another column here so that we can do this work. So equals x times the probability of x. And we copy that down, and we do that for all the prize amounts. And then we want to add all those up. Equals sum. And we get about 58.6 cents. So that's the average or the expected value. So let's picture what's going on with this ticket. It costs $1, so we go and we spend $1 for these tickets. And on average, what are we getting back out of those tickets after we spend our $1? Well, we're getting 58 cents. So the difference, so equals 1 minus the expected winnings on average. This is the take. This is the amount that the state gets in profit from selling each of these tickets. Now, actually, it's less than that, because when the government prints up these tickets, they have to pay to print the tickets. They have to give a commission to the stores that actually sell the tickets. And so the actual profit out of each dollar of revenue is actually less than 41 cents. After they pay all their expenses, it's probably about 30 cents that they get to keep as profit. And in North Carolina, this is an education lottery. And so this extra money, this profit, is supposed to go towards paying for schools and scholarships and things like that. So we're paying $1 on average, and we're getting 58.6 cents back in winnings on average. So what we're losing is about 41 cents for every ticket we buy. It's not a smart investment. Not a smart investment. If you actually want to use this as a retirement strategy, not a very good strategy. Now, again, another thing we might want to do is let's have a look at this variance formula here, and we can figure out what the variance and the standard deviation of this lottery ticket is. So let me... Okay, so I made these numbers a lot smaller. We actually don't need this column, since this is what we use to calculate the expected value. But we do need that expected value. So let's expand it just enough to where we can see that. Okay, so that 58.6 cents. So the variance formula says, take each value for x, the amount that we could possibly win here, subtract the mean, so the mean is that expected value of 0.586, square that difference, and then multiply it times the probability. And after you do that, add all those things up. Okay, so let's do that in this column over here and calculate the variance. So equals, in parentheses, x, 7,000 in this case, minus 0.586. And I'm going to put dollar signs on those so that it always looks at that value when we copy it down, squared, and then times the probability right here. Okay, now we can see the value. And then we copy this down. And so we see when we're calculating the variance that the largest part, the largest component of the variance is going to be this first entry. Because remember that variance is a way of measuring how spread out values are. And this $7,000 is such a large value, so spread out from the others, that really adds into this variance quite a bit. So we've taken each value, right? We subtracted the mean, we squared it, we multiplied it times the probability, and now the last step is to add all those things up. And that will give us the variance. 91.4, roughly. So that's the variance. Now, as I always say, the variance doesn't really tell you much, except that a bigger value of the variance means that it's more spread out. What we want to do is take the square root of that variance, and that will give us the standard deviation. Now this standard deviation, again, it's a bit difficult to interpret this with discrete probability distributions sometimes. But again, the standard deviation normally tells us a common distance that the values we will see are away from the mean. And so you could roughly, and again this is very roughly in this case, say, well, what do we expect to see when we scratch off this ticket? Well, most of the time we expect to win about 58.6 cents for a dollar investment, plus or minus $9.56. Now in this case that interpretation is very strained and doesn't make a whole lot of sense, because if we subtract $9.56, we're going into negative values, which are impossible for this particular ticket. And if we add $9.56 to the expected value, that's taking us up a little bit above $10. So you could very roughly interpret it as saying, well, what's going to happen most of the time when you play the scratch and win? You're going to win between $0 and $10. Now again, that's not extremely informative, because if you add up these probabilities, the 78% plus the 14% plus 4% plus 1.6% plus 0.6% and 0.7%, you're getting very close to 100% there. So almost all the time, that's what's going to happen. It doesn't really help our understanding of what's going on when we play this scratch and win ticket very much. But those are all the tricks. Those are all the things you can do when you analyze one of these scratch and wins. One of the most important things is, again, this number, to figure out, on average, how much do you expect to win. So again, in this case, the 0.5. Let me copy it down here so we can see it a little bit bigger. That 0.586 cents is the long run expected value. So to be more precise, what if we bought every single one of these tickets, every single one of these 10,560,000 tickets? Then on average, for every dollar that we spent buying these tickets, we would be getting about 58.6 cents back. So we can get an estimate of how much money, if the government sells all of these lottery tickets, how much money will it bring in net revenue, not including their expenses. Well, the net revenue is going to be this 41.3 cents that they get for each ticket. Let me get this to where we can actually see it. The 41.3 cents they get for each ticket. So if we take that and multiply it times that 10 million number over here, let me just pick one of those. Then for this one lottery ticket, we're going to see the net revenue is about $4,370,208. So I apologize for Excel making life so hard talking about this. Okay, so $4,370,000 roughly. And again, they're going to have to pay some expenses to print the tickets, distribute the tickets, and have gas stations and grocery stores sell these tickets. But you could get an idea about how profitable an enterprise this actually is. Now, in the next couple of videos, we're going to continue looking at lottery tickets, but we're going to look at some of these other kinds of lottery tickets that they have. Up next, we're going to look at the games they call Pick 3 and Pick 4. And the Pick 3 and Pick 4 games, what they do is you pick, say, 3 numbers between 0 and 9, and when they see who wins. They pick 3 balls out of 3 different buckets. So they pick 1 ball out of one bucket, 1 ball out of a second bucket, a 3rd ball out of a 3rd bucket. And so you can have, say you could pick 1-1-1. That's possible because there's a ping pong ball with the number 1 in the 1st bucket and in the 2nd bucket and in the 3rd bucket. So stay tuned and see how you can use these discrete probability distribution formulas to analyze pick 3 and pick 4 type games.